Pleasant day to everyone. Today we're going to discuss part 4 of Module 6, Fitting Curves and Interpolation. In this lecture, we're going to discuss finite differences. Finite differences is defined as a numerical method which approximates derivatives of differential equations. Polynomials can be determined by identifying the degree of difference and overlapping the equations with the values in a dataset. There are two ways of creating a difference table, and that is by forward and backward difference. To understand finite differences, we start off first with checking for the patterns in a given dataset. So we start off first with x sub o, followed by x sub 1, x sub 2, x sub 3, until the last given point, which is x sub n. Checking now for the difference between x sub o and x sub 1, and x sub 1 and x sub 2, x sub 2 and x sub 3, and so on, which is given by each. And if we have the h for each of the intervals as equal values, then we could correlate a function or an equation that would have that could be written as x sub 1 equal to x sub o plus h. And for x sub 2, we could write this as x sub 2 equal to x sub o plus 2h, or x sub 1 plus h. And for x sub 3, this could also be written as x sub o plus 3h, or x sub 2 plus h. So if we're going to consider now the pattern of our equations, we could write a general form for x sub n, or any value of x, can now be solved as x sub n is equal to x sub o plus n times h, or x sub n is equal to x sub n minus 1 plus h. Given now that y is a function of x, we could also write the pattern of the equations of y for each value of x as y(o) is equal to fxo, or for y1, that is the function of x sub 1. Then we have y2 is equal to the function of x2, and y3 is equal to the function of x3. And for any value of x, we can now write that its equivalent y is a function of x sub n. So for finite differences, the values of x is considered as our input or our argument, and the values of y, which is the result as a function of the x, is what we call our entries. As we have said in our introduction, finite differences can be determined in two ways. So let's start off first with the forward difference. For forward difference, this is now denoted as delta of f of x, wherein delta would simply mean a change in value, or the difference in value of the functions of x. So for the pattern of the forward difference, let us take delta f of xo is equal to f of x sub o plus h minus the f of x sub o, wherein we could take note that the first term is the next or the preceding value, and f of x sub o is the present or the current value. Again, for the next value of x, which is x sub 1, we could write that the delta of f of x sub 1 is equal to the function of x sub 1 plus h minus f of x sub 1. Likewise, for this next term, the delta of function of x sub 2 is equal to the function of x sub 2 plus h minus the function of x sub 2. Writing this now in terms of y, we have delta of y sub o is equal to y1 minus y sub o, and delta of y sub 1 is equal to y2 minus y1, and the delta of y2 is equal to y3 minus y2. Given now these equations, we call this as the first forward differences, or the difference of the first values of y. And we have what we call the second forward differences, which is now taken as the second difference of y sub o is equal to delta y1 minus delta yo, and the second difference of y1 is equal to delta y2 minus delta y1, and delta 2, or second difference of y sub 2 is equal to delta y3 minus delta y2. So if we're going to get the third forward difference, that would simply be the difference of the previous differences. So to understand the pattern that we have just derived, let us take a look at this table. So given now the values of x and its equivalent y, delta y can simply be taken as y1 minus y sub o. Delta y sub 1 is equal to y2 minus 1, y1. Delta y2 is equal to y3 minus y2. Delta y3 is equal to y4 minus y3, and so on. For the second difference, we'll have now the difference of delta y, and that is delta 2y sub o is equal to delta y1 minus delta y sub o. Second difference of y1 is equal to delta y2 minus delta y1, and the second difference of y sub 2 is equal to delta y3 minus delta y2. And if we want to get the third difference, that will now be the difference of the second forward difference, and it will give us delta 3yo is equal to the second difference of y1 minus the second difference of yo, and we have the third difference of y1 is equal to the second difference of y2 minus the second difference of y1. So the first terms for each difference is what we call your leading forward differences. The second way of determining your finite difference is what we call the backward difference, which is denoted as delta f of x. Same as for, or almost the same with forward difference, we also have what we call your first backward differences, wherein we have nabla of y1 is equal to y1 minus y sub o, wherein this will now be the present value minus the previous or preceding value. And then nabla y sub 2 is equal to y sub 2 minus y1. And we have nabla y3 is equal to y3 minus y2. For the second backward differences, it is same as for the forward difference. So nabla squared y is taken as nabla squared y sub 1 is equal to nabla y sub 1 minus nabla y sub o. Nabla squared y sub 2 is equal to nabla y2 minus nabla y sub 1. and nabla squared y sub 3 is equal to nabla y3 minus nabla y2. In tabular form, we could now write or solve for the backward difference. Given now the values of x and y, we can solve for nabla y as y1 minus y sub o. We have y nabla y2 is equal to y2 minus y1. And we have nabla y3 is equal to y3 minus 2. And nabla y4 is equal to y4 minus y3. Getting now the difference of the first nabla, we get nabla squared of y, wherein nabla squared y sub 1 is equal to nabla y1 minus nabla y sub o. Nabla squared y2 is equal to nabla y2 minus nabla y1. Nabla squared y3 is equal to nabla y3 minus nabla y2. And again, taking the difference of the second backward difference, we get nabla cube of y is now nabla cube y1 is equal to nabla squared y1 minus nabla squared y0, and nabla cube of y1 or y2 is equal to nabla y2 minus nabla y1, wherein the last terms or the last difference in the table would be what we call your leading backward differences. Given a set of points or data, we can determine the equation that would best describe the relationship of x and y using finite differences. So to start off, we tabulate x, y, and then solve for the first difference. So we'll have 83 minus 15 is equal to 68. 519 minus 83 will give us 436. 1659 minus 519 is equal to 1140. 3839 minus 1659 is equal to 2180. And 7395 minus 3839 is equal to 3556. So next step is to determine the second difference by simply taking the differences of the first difference. So we have now 436 minus 68, which is equal to 368, followed by 1140 minus 436 is 704. 2180 minus 1140 is 1040. And 3556 minus 2180 is 1376. And then we solve for the next difference by 368 and 704, which is 336. 1040 minus 704 is 336. And 1376 minus 1040 is also 336. So taking now the next difference or the fourth difference of y will now give us 0 and 0. Since the fourth delta of y will now be equivalent to 0, we could now say that our last term would be delta cube of y. From here, we could now define that the equation will be equal to f of x is equal to ax cubed plus bx squared plus cx plus d. So since we have ended on the third delta, therefore, as we have said, the function of x will now be in the third degree. Therefore, in order to solve now for the coefficients a, b, c, and d, we apply the function of x with respect to our values of x. So we'll have now a times 1 cubed plus b times 1 squared plus c times 1 plus d is simply a plus b plus c plus d. For y of x equal to 2, we'll have now 8a plus 4b plus 2c plus d. And substituting 3 in this equation, we get 27a plus 9b plus 3c plus d. And then 4 is equal to 64a plus 16b plus 4c plus d. And for x equal to 5, we'll have y is equal to 125a plus 25b plus 5c plus d. And for x equal to 6 will be 216a plus 36b plus 6c plus d. So next we get delta y. So we'll have 7a plus 3b plus c, followed by 19a plus 5b plus c. Next, we have 37a plus b plus c. Then we have 61a plus 9b plus c. And lastly, we have 91a plus 11b plus c. Then we move on to the second degree of delta. So we get 19a minus 7a is 12a plus 2b. Then we get 18a plus 2b, 24a plus 2b, and 30a plus 9b. And for the third degree of delta y, we get 6a for all of our delta. So again, if we continue with the fourth degree of delta y, we will get a value of 0. Overlapping the equations that we have derived from the previous slides, we get the following terms. And overlapping this with the values that we have solved in the first step, we get the following equations for each value of y and delta y. In order to solve now for our coefficients a, b, c, and d, we could solve this using the different equations. And to have a simpler solution, we now use those equations with the smaller coefficient values. So with this, we start off with the third degree of y, which is given as 6a equal to 336, thus giving us a value of a equal to 56. Moving on to the next equation, which is 12a plus 2b equal to 368. From the second degree of y, we get now 12 times 56 plus 2b equal to 368, which will give us a value of b equal to negative 152. For delta y, we have 7a plus 3b plus c equal to 68. And substituting the value of a and b, we get 7 times 56 plus 3 times negative 152 plus c equal to 68, which will now have a value of c equal to 132. And lastly, for y, we have a plus b plus c plus d equal to 15. And substituting the value of a, b, and c, we get a value of d equal to negative 21. So therefore, our equation that would best describe the given data set is the function of x, which is equal to y, is equal to 56 x cubed minus 152x squared plus 132x minus 21. So as a review for finite differences, we have two ways of determining the differences of data sets, we have the forward differences, wherein delta is taken as the difference of the next or the proceeding value minus the present value or the current value, and the backward differences, which is taken as nabla and is the difference of the present value and the previous value. For the degree of the equation, it would now depend on the degree of the computed delta or nabla. So if we reach a value of 0 or we have attained a single equation for our delta or nabla, we will now follow the degree from which we have stopped. For example, if we have stopped at delta y, therefore the function of x now will be the first degree equation, which is equal to ax plus b. If we stop at the second degree of delta, then the function of x will follow a second degree equation, or will follow the format ax squared plus bx plus c. Likewise, if we have a third degree of y for the delta, it will also follow a third degree of the equation, ax cubed plus bx squared plus cx plus d, and so on. So that's it for the introduction for finite differences. Thank you for listening.